recording and officially open the fall session of VSA Online webinar series. So welcome everybody. So it's my great pleasure to invite you all and see you all coming. So it's really kind of becoming a tradition. So you probably check the program on the web. So we have prepared an exciting program for this season. So there are a few vacant slots. So if you want to present a talk or something, so you know how to find me. So please drop me a line by email. Also, those of you who are online, so I want to say it loud, but I will send a separate email announcing a work in progress session. So in December. So it was an idea coined by Rose Geller, who said, why not to organize a work in progress session? So a session with very short talks by people just describing the current work on VSA or HDC. So I think it's an interesting idea. So let's see if we will make it happen. So let's hope that we will make it happen. So so prepare some interesting ideas for the last session, last webinar of the fall session, which will happen in December. But as I told you, I will announce. I will send the announcement in a separate email. But for now, I should stop talking and welcome Graham Bent from and his co-workers from Cardiff University to open our fall season. So Graham, please, the floor is yours.
Thank you. Thanks, Evgeny. So well, welcome everyone. The talk this evening is on hyperdimensional computing using time-to-spike neuromorphic circuits. And this is work with my co-authors, Chris Simpkin, Yuha Lee, and Alan Preece from Cardiff University. The work that we were doing was done as part of a bilateral UK-US research program called the DEUS ITA. And our sponsors for that were the DSTL laboratory from UK MOD and the DEVCOM Army Research Laboratory in the United States. So, one second, I just, oops. So I just wanted to say something about the motivation for our work. Then you'll get the context for this work that we've been doing with spiking neural networks. But the basic idea was, I presented this a couple of years ago to this forum. And the basic idea was to use hyperdimensional computing or these large hypervectors to be able to do service discovery and workflow orchestration in distributed communications networks with low bandwidth communications. And the basic idea was that we formulated a workflow using the vector representation and using a hierarchical binding scheme to be able to represent complex workflows. And the vectors themselves were semantic vectors which were generated in a semantic vector space. And by binding and bundling them together, we could actually produce a single vector that could be transmitted into a communications network and then passed around the communications network, being unbound at various stages in the network to both discover the services that you wanted to communicate together and orchestrate the whole communications and the workflow. And that's been a very successful project so far. The techniques that we use were the standard techniques that we're all familiar with hyperdimensional computing or vector symbolic architectures. And essentially what we require is sort of shown here on the upper left of the diagram. We need the following components. We need a way of generating our vectors in the first place. We need techniques for vector binding. We need the ability to do bundling of vectors. We need to be able to do the unbinding steps. And we need cleanup memory so that we can regenerate the vector from the noisy unbound vector that we get at the end of the process, so that we can either get an index to a clean version of the vector, or we can use the index for other or stimulating other processes. And as I mentioned, in our particular work, we were using a hierarchical binding scheme, which was sort of unbounded in the depth to which you could perform these binding operations. But basically, we're able to go from very low level symbolic vectors, creating higher and higher level vectors using a combination of cyclic shift and role filler binding operations. But the nice thing about the hierarchy, and I think if you remember those who were on the presentation last time, we actually used Shakespeare's Hamlet to sort of demonstrate how this worked by having individual words down as the base symbols and working our way up through scenes and acts and so on up to a vector that represented the whole of the Hamlet play. And then you could transmit that vector and unbind it and work your way back through the acts and the scenes down to the individual stanzas and the words that were spoken, just to demonstrate how the hierarchical binding scheme worked. Now, all of our previous work, we've been using hypervectors with a dense encoding, basically large binary vectors, typically with a dimension of 10,000 bits. And we've been using this hypervector representation to perform all of the work that we've done so far. But one of the things that we were interested in was whether or not we could come up with a more energy efficient way of representing the vectors by coming up with some sparse vector encoding, so that instead of having 10 kilobits with approximately 50% of the bits set to 1, we could actually have much fewer bits to represent the whole vector. And that's what I'm going to focus on this evening. So the encoding scheme that we looked at was one that was suggested back in 2015 by Leho and others. And Penty was one of the authors of this paper. And the slot encoding model is a very simple model. Essentially, you have a set of slots, and within each slot, you have a number of bit positions, and you can set 1 bit in each of the slots. And using this slot encoding, you can do the 2 basic binding operations that we want to use. You can do a cyclic shift binding, which is simply a cyclic shift of each of the slots. So you simply move the slots around in a cyclic shift. And role filler binding is simply taking the bit position for your 2 vectors. So if you take slot 1, you have bit position 1 in slot in for vector 1. The equivalent slot in vector 2, you have another bit position. And in the bound vector, the binding process just adds the bit positions and takes the modulus of the number of bits. So I've just used an example here where we've only got 10 bits per slot, but you add the 2 together and you end up with the bit at position 3, for example. So those are the 2 simple binding operations. And the bundling operation is equally simple. Essentially, you just add the vectors together. You then have a pattern with the sum in each of the slots, and you essentially compute the argmax. And so where you've got the most bits in the vector, you make the vector sparse by just selecting that bit position. So that was the Leho model that was presented in 2015. And we thought that was a good starting point to see whether or not we could implement this in a spiking neural network, because it's an easy mapping to a neuron model. Essentially, each slot becomes a neuron, and each bit becomes the time to spike within each cycle of the binding or bundling operations. And I'm going to show you that as we go through this evening. Now, one of the important questions is, if we use this encoding, this slot encoding model, how does it compare with the but the bundling capacity that we get for our standard BSC encoding. And it turns out that if we were to take a BSC vector with dimension D, say 10,000 bits, then the equivalent, it turns out, for the slot encoding model is that D equals M, where M are the number of slots, log to the base 2 of the number of possible bit positions. And that's been demonstrated both theoretically and empirically in some of the papers that we've written. And here I'm just showing the result of that by comparing the BSC vector and the slot encoding for two cases, one where we have a library size of 1,000 vectors and one where we have a library size of 10,000 vectors. And you can see that the number of vectors that we can bundle together is in the region of 50 when we go for an error of 1 in 10 to the -6. Now, we put this graph in one of our early papers, and we got a very negative review about this. In fact, what the reviewer said was that our bundling capacity was dismal. But I think they misunderstood what our motivating application was. In our motivating application, we want extremely high accuracy. We want an error rate of around 1 in 10 to the 6. And so with that sort of error rate, as Dennis Clayco and Penty and others have pointed out, you would expect to be able to bind with a 10 kilobit vector, something in the region of 89 vectors, and still be able to recover all 89 vectors with an error of 1 in 10 to the 6. And that's essentially what we're showing here. The interesting thing is that this relationship with the sparse encoding, m log to the base 2 of the number of bits, is very interesting, because if you want to transmit this vector over a communications network, what it's telling you is that it costs you exactly the same in terms of the number of bits to transmit either a 10 kilobit vector or a sparse vector. In other words, the cost of transmitting the information is the same. But the bundling capacity is not dismal. In fact, the bundling capacity is exactly what you would expect. And in fact, what we did was to show that if you go for a lower accuracy, so as you reduce the accuracy, then the bundling capacity follows the form that we see here. And here we've just taken different representations of M and the number of bits, just to show what happens as you change either the number of slots or you change the number of possible bits per slot. And what you can see is that we get an accuracy that falls off, leading to bundling capacities in the region of a couple of thousand if you want to accept a 20% error rate. And that's exactly what's been reported by others. Here's an example from a paper from 2018, written by Paxson and Dennis anyway, they showed that if you have a small library size, here they've just essentially chosen an alphabet with 27 symbols, that the number of items that you can store for an HDC vector varies as you change the dimension of the vector. So we're in this region here, typically 10,000. So we're between these two curves here, and you can see for a 60% accuracy, you'd get around 2,000 vectors. And in fact, here, if we set our library size to 27, we're in exactly the same sort of region for the sparse encoding model. So we don't have a dismal bundling capacity. It's exactly the same as everyone else has been reporting using other schemes, whether we use HDC or we use any other representation for the vectors. So let's turn back to what we're trying to do here. And what we're trying to do is to represent our vectors in a neuromorphic processing model. And the neuromorphic processing model that we tried to work towards was one based on IBM's True North processor. Now, for those of you not familiar with the IBM True North processor, what I've got here is a sort of schematic of how they've arranged the processing elements on a True North chip. And essentially what you have are blocks that contain a number of neurons, and here's the output of the neuron. And each neuron has a crossbar scheme where the vertical crossbar represents a dendrite and the horizontal crossbar represents an axon. And so you can connect neurons together by taking the output and connecting it to an axon, either in the same block or in different blocks on the chip. And at each point where you want to have a connection between an axon and a dendrite, just as in the sort of biological model, you have a synaptic connection, and you program the device by defining where the synaptic connections are. You can delay the spike at the input to each axon, and the processing model essentially works by taking spikes and passing the spikes to axons, either in the same block or on other blocks, either on the same chip or on adjacent chips. So you can have multiple chips on a single board. And this diagram here actually shows the idea of the spikes moving around. In order to make this a programmable model in True North, it's not an actual spike, but it's a very small 12-bit message. And the 12-bit message basically tells the output from a particular neuron how many spaces, either north, south, east, or west from that neuron, you actually transmit the spike so that it arrives at the appropriate axon, again, either in the same block or in another block or in a block on an adjacent chip. Now, the reason I'm showing you this is because I'm going to use a similar sort of diagram to illustrate how we implemented this sort of sparse vector encoding not on the True North chip itself, but on a Brian 2 simulation of a True North chip, or a True North chip with some modifications, and I'll try and explain that as we go through. So let's look at the different components that we need for a VSA or hyperdimensional computing scheme. We've already seen we need vector generation, vector binding, bundling, unbinding, and cleanup memory. I want to show you how we implement each of these different components. So let's start off with the vector generation. And so vector generation is very straightforward. Essentially, we take this sort of idea of a True North chip, but what the True North chip doesn't allow you to do is to have delays on each synapse. You can have a delay on the input to this axon, but you can't have a delay on each synaptic connection, which is a pity, because that's what we've made the assumption that we can do, because it turns out that that's a very easy way to generate your vectors. So if we think of our vector as this group of neurons, where the group of neurons is essentially the number of slots in our scheme, and the time to spike is the number of bit positions, then what we're showing here is that if we want to generate a vector, we can store all the vectors that we want to use by having different time delays on each synapse dendrite connection. And if we just trigger a single, what I've called a P neuron here, that P neuron spike is delayed at this synapse and then arrives at the neuron after the delay. And so here we've got a delay D0, D1, and so on across the array here. And that will generate a sequence of spikes where we have one spike per slot, per neuron in each time slot. And what you see then will be an output. And here's just for illustration, we've implemented this in the Brian 2 simulator. This is an output from the Brian 2 simulator itself. And here I've just chosen 100 neurons and 100 bit positions per slot, just to sort of illustrate what's going on. But you do a single trigger and you generate a pattern of this is the vector that you get in terms of time delays for each neuron. So that's how you generate a vector. But how, before I go on to talk about the binding and bundling and unbinding, I want to talk about how we reproduce that vector, how we do the cleanup memory, because normally once we bundle a number of vectors together, what we actually get as we unbind is a noisy version of the vector. But I want to show you with a sort of clean version of the vector what actually happens for cleanup memory. And so this is the cleanup memory, and you'll see that it looks very similar to the generation, vector generation. But what we've actually done is, here's the input vector now, the one that we just generated. We input the vector now into an array where here we have the dendrites for the output neurons, and here are the axons for each neuron from the vector. And now the synaptic time delays here are just B delta minus D0. If we want this to be the corresponding vector to our input vector, we have B delta minus D0 here, B delta minus D1 here, and so on. So this vector, what that means is that if a spike comes in with a time delay of D0, it will be delayed by a further time, B delta minus D0, so it will arrive at this neuron at a time B delta after T0. So each input here arrives at this G5 neuron at exactly the same time at B delta. Whereas if each of these spikes hits another neuron with different time delays, random time delays, because these vectors are orthogonal, then what you get from all the other vectors is just noise. And that's what we're showing here in the Brian2 simulation. So here we've got a vector at time T0, another vector at time T1, another at time T2, and so on. And what happens is when we feed this vector in at time T0, then for all the other neurons, that's what we're seeing here in all these different colors, it's just random when they add their voltages together. But for the neuron that matches, they all add together at the same time at B delta in this particular case, 100 milliseconds. And you can see that we get essentially the same voltage, but with some noise. But here's the expected value from the theory, and you can see that the expected value is, and the values we actually get are around the expectation value. So what happens is that the output here, you remember we put them in, if I just go back a couple, if we put them in the order T0, T1, T2, T3, T4, and so on, if we put them in that order, then in this particular case, when we put in vector T1, we get a vector T1 coming out, or the neuron corresponding to vector T1 fires, then T2, T3, T4, and T5. So that's how the cleanup memory works. I want to show you that because we'll use this a number of times as we go through the presentation. So what about vector binding and bundling? Well, we wanted to, first of all, implement the Lehel model just to show that we could do that. And if you remember, for the Lehel model, there are two types of binding operation. I'm just going to show you the cyclic shift operation for the moment. I'll show you the role filler binding later on, but for a slightly different variant of the Lehel model. So here we've got our vector generation. If we want to do cyclic shift, then essentially all we do is we take our neuron group, again of length m, where m is the number of neurons, and we connect neuron 1 to neuron 2, the output of neuron 2 to the input of neuron 3, and so on. And then finally, the output of this neuron goes back to the input of the first neuron. So that's the cyclic shift operation. It's just a chain of neurons. in order to perform the argmax operation, we need 2 extra groups of neurons, and I'll show you what those neuron groups do in a moment to compute the argmax. But what we want to get out of this process is a sparse vector with still only 1 bit per slot, so that when we trigger a vector here, so we trigger a vector, it's cyclically shifted. 1 time cycle later, we introduce another vector. That vector gets summed together with the previous vector, and I'll show you this in a moment in the Brian 2 simulations. But here we're just going to trigger a sequence of vectors. We're actually going to start with a vector up here and trigger them in this direction. They're going to be cyclically shifted, added together. The argmax is going to be computed, and we're going to get a sparse vector out at the end. That's the basic processing. So it turns out that using the full Leho model, it gets quite complicated. And so here are vectors being generated. These are the P neurons. So these are single spikes being injected in on each cycle. And when we inject the first vector, we get, in the first 100 milliseconds, we get a single vector. In the next 100 milliseconds, we add the 2 vectors together. So we take the first vector, it's been cyclically shifted by 1 neuron position, and then we add in the next vector. And then 1 cycle later, we add in the next vector. So you'll see it gets denser and denser and denser as we go through the process. That's not really desirable. We'd really like to maintain the sparsity, but because we've got to do an argmax, we've got to do this in order to work out where multiple spikes occur in the same slot at the same bit position. Now you can see the same thing here, looking at the neuron voltage on just one of these neurons. So we've chosen neuron 16, which is around here somewhere. And what you can see is that in the first 100 milliseconds, we get 1 spike. In the next 100 milliseconds, 2 spikes. The next 100, 3, and so on. In this period here, we get 1 spike, then we get 2 spikes at the same time, and then 3, 4, 5 spikes. And if you look at what we've called the G1, this is the output from the G1 layer. If I just go back, you can see where the G1 layer is. What we get then is at the end of this time period, between 400 and 500 milliseconds, what we get are 5 spikes. We get an output spike here at about 455 milliseconds, the 2 spikes corresponding to this position here, and we get the other 3 spikes at the end. Now, we want to apply the argmax operator, so the question is, how do we do that? And what we do is if we look at the G2 neuron, just to remind you where the G2 neurons are, that's this layer here. What we do, here's the neuron voltage. So when we get the single spike, we get a 1 volt output. It doesn't have to be 1 volt. They've just used 1 volt to represent, so we can see it could be 1 millivolt or 1 microvolt. When we get the 2 spikes, we get something just above 1.5 volts, and then we get back down to the 1 volts here. In order to do the argmax, we have to change the threshold on the neuron. So this gets quite complicated. The neuron threshold, when it's going to fire, after the first firing gets increased to slightly above 1 volt. And then when it fires again, it gets increased to slightly above 2 volts. There are relatively easy ways to do this in the Brian 2 simulator, but essentially, I just want to show you how we would implement the Leho model with the argmax. But what you see happens at the output is that we just get a spike corresponding to the first threshold crossing, but then we get a second spike, which corresponds to the two spike voltage, but we don't get any spikes because these spikes have got a lower voltage. If we had 3 bits aligning at some point here, we'd get a spike at about 3 volts, and that would exceed this threshold. So we would have got a further spike here. And what we then do, in order just to end up with a single spike output, we take another layer, which is this G3 layer of neurons, and all that layer does is it's just a simple decaying neuron model. So it starts off at 1 volt, it decays until it hits the first spike hits. When it gets reset to 1 volt, it decays again. If there isn't a further spike, it would just decay and fire at 455 milliseconds, but there is a second spike, so it decays and fires at around 460 milliseconds, and you get a single spike output. So essentially what happens is this mess of spikes here ends up with a much simpler output, a sparse output. So we're taking multiple vectors, feeding them in, cyclically shifting, applying the argmax, and we get this nice sparse output vector. And if we feed that sparse output vector into our cleanup memory, then what we get is, here's the sparse vector, and we now do an unbinding process where we have a left cyclic shift. So rather than neuron 1 connecting to neuron 2, neuron 1 connects to neuron M, and neuron M feeds back to neuron 1. So we have this left cyclic shift process, which is just a linked list of neurons, but working in the opposite direction. So what happens is the bound vector, which is here, now the first time we see it, it looks like vector 0, because here's the spike in the cleanup memory. At 200 milliseconds, it looks like vector 2 and vector 3 and vector 4. So these vectors here, these neurons here, spike in this particular sequence, as you can see. So we fed in a sequence that went 4, 3, 2, 1, and it came out as 1, 2, 3, 4, because we're reversing the cyclic shift operation. Now that's all very well, but the problem with the model is that we have to, if I go back here, we get a very dense number of spikes. And of course, as you increase this to many, if you get up to 89 spikes, then we get an extremely dense vector. And that's not desirable. We want to maintain the sparsity. Also, in order for this to work, you've got to wait until you've got to know how many vectors you want to bind, so that you only apply the argmax function at the end of the process. And that means that this G3 layer of neurons at the end is only applied to that last bound vector. And that it all gets very messy. So what we wanted to do was to say, could we come up with a simpler model that didn't use the argmax? Because if we can do that, then what we can do is we can do incremental binding and bundling, which is a very desirable property. We don't want to have to wait until we bound, say, 10 or 100 or 80 vectors before we actually apply an argmax to get back to a sparse vector. We like to keep the vector sparse in every cycle. And the question is, well, what would happen if instead of using the argmax, we do exactly the same cyclic shift binding and bundling, but the bundling operation itself now is very simple. What we're going to do is we're just going to take the time of the earliest spike in each slot. So this is a single, we take this as a single slot. We have a bit at this position. We have another vector with a bit at this position. We're just going to take the time of the earliest vector. If we add in another vector, then we're going to take the time of that one. If we add in another vector, we still use the same time position. Just take the time of the earliest spike. And that's implemented very, very simply in a neuron model. But the question is, do we lose anything in terms of bundling capacity? And the answer to that is no, we don't. I've put binding capacity, it should be bundling capacity. But here you can see that the LAHO model with the argmax and what we've called LAHO X, which is just taking the earliest spike, are identical. So we're not losing anything by not performing the argmax function. And if anybody's got any comments about that later on, we can talk about that. So what that means is we can simplify our binding and bundling operations by only needing one layer of neurons. So here's the cyclic shift operation again. Here's our library. We put in we trigger a sequence of vectors that we want to bundle together. We perform a cyclic shift operation after each vector is generated, and we simply sum the outputs, but we take the earliest time to spike. So you can see that here. I'm just using it as an example, just 4 vectors, so you can see what happens. We trigger with vector 4. Here's the vector 4 that we trigger. If we just look at a single neuron in that group, a G2 neuron, it spikes at somewhere around about 90 milliseconds. In the next 100 milliseconds, we get 2 spikes. But the first spike is the one that triggers. The second spike produces a voltage, but you'll notice if you look very carefully that it's just a decay here. So it doesn't spike. It's only when you get a vertical line that you get the spike. So in each 100 millisecond time period, it's the first spike that we use. And that produces a vector in the first 100 milliseconds. The next vector is equal sparsity. We maintain the sparsity. But interestingly, as you increase the number of vectors that are bundled together, you'll notice that the time of the last spike gradually moves towards the beginning of the cycle. So we're actually getting some sort of compression going on here, where we don't need the full B or B delta bits in order to represent the vector. And as you go to more and more vectors, that becomes more and more enhanced, which is an interesting observation from these results. So does it work? Well, if we take that vector, we just take this last vector here, and we feed it into our unbinding circuit, where you remember we just run the process in reverse. Here's the first vector. You can see, if you look very carefully, that this vector is gradually moving as we move across. But here's the cleanup memory, and here's the result. As we unbind the vector, remember we fed it in as 4, 3, 2, 1. It unbinds in the opposite direction, and the output neurons fire in the order 0, 0, 1, 2, 3, 4, as we would expect. And again, here's the expectation value, and here are the actual voltages that we measure on the neurons. So that's cyclic shift binding, very simple model. What do we do about roll filler binding? Well, if you remember, for the roll filler binding, what we want to be able to do is to take the input from 2, this is for a single slot. We want to take the input from one vector and the other vector, and the binding operation is simply adding them together, modulus the time delay, modulus the number of bit positions. And the unbinding operation is the reverse. We want to be able to take the time between the two, again, mod B. And it turns out that we can do that in a very simple way, a very simple neuron model. I've used a linear voltage model here, but you could have an exponential increase and decrease. But essentially, all you do for binding is when the neuron, at the beginning of each cycle, the neuron basically increases its voltage. When it receives the first spike, it holds the voltage constant. And then when it receives the second spike, it decays back down to the 0 level. And at the 0 level, it can either spike, or you can use that to then cause it to increase until it hits an upper threshold. And then in the next 100 milliseconds, you'd get a spike at T1 plus T2 mod B. So basically, the neuron increases its voltage until the first spike, holds it constant, and then decreases after the second spike. And then we can use this operation if we want to get this exact T1 plus T2 mod B. You'll see in a moment we don't actually need to do this second step. We can just use the first step, but I'll come back to that. The unbinding operation, where we want to take, say, a bundle vector, and then we want to take the difference mod B. All we do this time is the neuron increases its voltage to the first spike, holds it constant, but then instead of decaying, it continues to increase the voltage until it hits the upper threshold, and we get T2 minus T1 mod B, which is exactly what we want. So it's a very simple neural model. It's just a leaky integrate and fire model, but with a slight variation between the binding and the unbinding operation. So here we've implemented it. Again, we're going to take our vector generation memory, but now we want to have roll vectors and filler vectors. So what we've done here is the first neuron we've treated as roll 1, the second neuron as the filler 1, the next one as roll 2 and filler 2, and so on. So these things fire together. So the roll and filler fire together, and this layer of neurons performs the binding operation, and the second layer of neurons takes the earliest spike. As you see here, the bundling operation takes the time of the earliest spike. And so here is what we're just running this through. You get 2 spikes at time 0, the roll 1 and filler 1, roll 2 and filler 2, roll 3 and filler 3. You can see the voltages on one of the G1 neurons. That produces a sequence of spikes, but we want to take the earliest spike, and so we get the earliest spike in each cycle, and this is the resulting vector that we get. So this is doing incremental roll filler binding and bundling as we move through the sequence. And again, notice that as we go through the sequence, the resulting vector gets compressed in the time slot. If we now take that resulting vector, that resulting bundled vector, and we now want to unbind it, what we do is we store the bundled vector into our memory, and we're going to trigger the bundled vector each time we trigger one of the filler vectors. So here, every time we trigger the bundled vector, and then we trigger roll 0, roll 1, roll 2, roll 3, here's the resulting voltage, and what comes out are these vectors here. We've separated them, we've done it over 200 millisecond periods, so you can see what's going on. And what you now get is the noise, and here is the spike corresponding to the whichever neuron fires here. And what you see is we now pull out, but when we fire with roll 1, we get filler 1. When we fire with roll 2, we get filler 2. So we can unbind roll and filler vectors. So we're nearly there. How can we use this in our motivating example? And if you remember, in our motivating example, we use this hierarchical binding scheme. And the hierarchical binding scheme, in order to do that, we need a combination of roll filler binding with cyclic shift. And in our representation here, the P0 will be a position vector. The exponent here is the number of cyclic shift operations we performed on the vectors. I'm not going to go all the detail about this, but at each level, you have what we call a T vector plus the bundled vector that we want to represent our workflow or whatever it is we're using. And one of the questions that's been asked by some of the reviewers were, well, how do you use this in operation? You've got all these VSA operations you can perform on the spiking neural networks, but how do you actually do any flow control? Well, what we want to do here is we want to input a vector, and then we want that vector to unbind itself and look like B1, and then B1 to unbind itself and look like C1, and C1 to unbind itself and look like M0, and then as we unbind it, it steps through here back up to C2 and so on. How do we do that? Well, one way of doing it is shown here. Essentially, we have our workflow vector, which is this ZX vector here, which is comprised of role filler pairs with cyclic shifts. And what we do in the memory here is we store all the possible position vectors shifted by a number of positions, so cyclically shifted. And what we store in our cleanup memory, rather than use it as a cleanup memory, we actually store the permuted T vector. So each time we unbind, we permute the T vector. So initially, we'll get the T vector. So if we pass the workflow vector and bind it with a null vector, we use a cyclic shift operation and a subtraction unbinding operation. What happens the first time is we just get the T vector, but we feed the T vector back to get the P0 vector, which is the one that we need to unbind the next step. That automatically unbinds the next step, and that fires this particular step here. So what happens is we get two things happening at each step then. Initially, we just get the T vector, but on the next step, we get the next, we get the permuted T vector, and we get the output for Z1 because they're superposed. So we get two spikes, one for the vector that we want to unbind and one for the vector that we need to do the next unbinding step. And so the whole thing just cycles around and works its way down through the hierarchy, as I've shown you. So that just gives you a feel for the way in which you can use these cleanup memory operations to actually perform flow control. So I'm coming to the conclusion now. What have we done? Well, in this presentation, we've demonstrated that hyperdimensional computing operations typical of VSA architectures can be implemented as time-to-spike neuromorphic circuits, and these circuits perform close to the theoretical predictions that we've obtained from a sparse vector encoding model, and they have similar performance to other encoding schemes. And I think this model has some interesting characteristics. I mean, first of all, the vector generation uses a library that can be stored using synaptic time delays on the dendrites of the neurons, and that they represent the vectors. And the vectors can be generated and selected just using a single spike on an axon that connects to those synapses. That's a very sort of, I think, biologically plausible model, which is interesting. And the cleanup memory is achieved using a symmetric process to the vector generation, and it produces a single output from the matching neuron, and we can use that to trigger the next action. So we've got a nice mechanism for flow control. It's a very simple bundling process. I mean, the earliest time to spike for each neuron is easily achieved using what are called the refractory properties of the neuron, which are things that the Brian 2 simulator has within it and can be easily achieved in a neuromorphic processor. The cyclic shift binding and unbinding are just linked chains of neurons, and the role filler binding use very simple integrate and fire neuron models, nothing complex in what we're doing. And the useful properties of this approach are that, first of all, when we compare with our previous work using BSC vectors, this relationship D equals M log 2B, where D is the BSC dimension and M is the number of neurons and B the number of bit positions, is a sort of general rule of thumb that we can apply. And of course, that means that if we want to communicate a vector between two locations, it's going to cost us the same in terms of the number of bits to represent the vector. The model also allows incremental binding and bundling, and I think that really is a significant advantage, particularly in a distributed communications environment. We don't need to gather the vectors together before we perform the bundling operation. And I think future neuromorphic processors, if we could get them to be able to represent time delays at the synapses, that would allow us to perform these VSA operations at extremely low powers. So in conclusion, the full capabilities that can be enabled by VSA operations in spiking neural network circuits, I think it's still to be explored. There's lots that we could still do, but I think it's clear from these initial results that using hyperdimensional or performing hyperdimensional computing using time to spike neuromorphic circuits does offer the potential to develop a new generation of very energy efficient artificial intelligence capabilities. So I'm going to end there. There are some references at the end. There are a couple of papers that we've written. One was at a conference that we write because our customer was a military customer. We had a paper at SPIE on energy efficient spiking neural networks for service workflow composition. And we recently presented a paper at the IJCNN 2022. It's yet to be published, but it is available on the Cardiff website, and there's a reference to that. And then all of these models that I presented this evening or this morning, wherever you are in the world, the Brian 2 code for those is available in Jupyter Notebooks, and there's a link to that. And then just finally, the acknowledgement is to our sponsors for this work, and thank you for your attention.
Graham, thank you very much indeed for your talk, very exciting talk. And so now I open the floor for questions. So I see there are some people working closely with neuromorphic implementation of VSA, so maybe, I mean, you will have some comments or questions. So to me, it appears as a slightly different approach anyways. So let's see.
Yeah, Graham, this is Fritz Sommer.
Yeah.
I have a question. So, or maybe a comment and a question. So, I don't know if you saw this. So we have a paper, Paxson and I, in 2019 in PNAS, where we actually also use these delay synapses to do cleanup. We do that a little bit different from how you do it. We do it in a recurrent associative memory, basically, but there's definitely some relation here. But then my other question is, so if you do this bundling by always using the earlier spike, you mentioned that you kind of do this compression. And how much actually does this hurt you in the bundling capacity? Did you somehow quantitatively explore that?
Yeah, it doesn't affect at all. That's the amazing.
So how can this be? I mean, you throw away information, right? So if you add basically two blocks that have two different spikes at two different times, and you, as I understand, you then just take the earlier spike. You kind of lost the information of the second. So how comes that this doesn't hurt you?
Because if you look at the Leho original paper that takes the argmax, it's about how many times these vectors are orthogonal, so that there's a very low probability that you're going to get multiple spikes at the same time. So using the argmax really doesn't give you any great advantage. Taking the earliest spike, because these are essentially random vectors, you could take.
Is this in a limit where you have so many blocks that basically it doesn't harm you to throw this information away?
That's right. We normally, well, again, in all the experiments we've done, it's not shown any loss of accuracy. And I mentioned this to Dennis. He asked for a copy of the paper, and he said he was going to have a look at it because he was equally surprised that we get this result. I'm not sure I've got a sort of analytical answer. It's something that I've been trying to work through, but it's a good question because I don't know the answer. All I know is that we don't lose any bundling capacity by using the time of the earliest spike.
My caveat to that answer, Graham, would just be, for sensible numbers of vectors, if you were trying to bundle up 10,000 vectors. Well, now we are going to get some coincidences, but for the type of capacity that matches with binary splatter codes, your comment about it's very unlikely for bits in the slots to line up is correct. So you don't throw much information away, because one of the other modes of choosing the winning bit is just to, if when you've done your summation everything's a 1, you can one algorithm is to choose a bit at random, and that's no different than taking the first spike.
Exactly. Yeah. So it's a really good question. It's a really good question. I don't know whether we've not got an analytical solution to that, although there must be one. But it's just very interesting that we don't lose any capacity.
Yeah, thank you.
More questions?
It's probably worth me saying that I have sort of reached out to some of my former IBM colleagues to see what their thoughts were on having a true north type device with time delays at each of the synaptic connections. And the general concern about that is that that can actually may not necessarily be a particularly energy efficient way of designing the chip. So that's an open question for the sort of designers of neuromorphic processors. But it would be really nice if we could have some sort of device where we could actually store the time delays at the synaptic connection. In terms of a biological model, which is interesting, you can imagine that in terms of a biological synapse, that'd be a relatively simple thing to do. It's only a sort of chemical concentration issue, really. So having variable delays at synapse, at the synapse between the axon and the dendrite, I would imagine would be a very plausible biological model.
Yeah, there's definitely other hardwares with which you can do it. I mean, for example, Loihi.
Yeah, well, I was gonna ask about whether we could implement something like this on Loihi.
Yeah, I mean, we implemented actually a small model of our 2019 paper with the delay synapses cleanup on Loihi.
So the archive of that is going online today, actually. I just should add that. So that might be interesting because the model seems very similar, actually, that we implement on Loihi, also using synaptic delays and a similar integration, a way of integrating to bind. But I mean, it's not exactly the same, but it's very similar.
Right.
Yeah.
That's actually, yeah. So this is a new paper. So you watch out on archive this Alpha. Yeah, thanks for this comment. I mean, I was talking about the 2019 paper, and there we have also a small simulation of a smaller network.
Alpha, if since you are talking about this, can you post the link to the chat?
Yeah, it's going online today
Oh.
in 4 hours. So
okay.
I can post the link via
but please send an email to the group. So I think it's interesting, and I mean, think,
unfortunately, I think we haven't cited yet the
Alpha,
the
maybe
results
just
presented today.
Alpha, can you just send us the title in the chat?
Yeah, sure, I will do that.
That would be, but I think it would be interesting really to see, because I mean that what you presented, Graham, it's a kind of I mean, to me it was first time I was seeing truly binary sparse codes being implemented on neuromorphic hardware or simulator. So that would be interesting to digest and reflect on this technique.
Well, because we've been using the dense hypervector representation for all our previous work, we did actually a couple of years ago work with Abbas Rahimi using their phase change memory device to try to do energy efficient binding and bundling, and that looked like very promising. But we wanted to explore whether we could do the same sort of thing using a sparse representation on a neuromorphic device, and try to sort of compare the two approaches. And they're very similar. I think you can make energy estimates based on the true north chip for how much energy is required to perform these operations, and it's very, very similar to the phase change memory device.
Yes.
Yeah, I may comment something, and that's about these slots where you have a single bit representing the value within a slot, and there definitely is relation to Tony Plate's holographic reduced representation in the time domain, and so he doesn't go into an implementation, but he deals with complex vectors and vectors of phasors. So yeah, they basically just, I think they sort of fundamentally the same thing.
Yeah, I think that's right, Pentti. It's just a phaser, isn't it? The bit position is just a phaser. So yeah, so it must be equivalent. So it's perhaps I should just have a look back at Tony's paper again and see what the equivalence is. I mean, I'm not claiming that what we're doing.
So there's a little bit of a difference in the bundling operation, right? So if you basically add two phasors, you just get another phasor. So it's always stays one sparse. It's all fine. And with the binding. With the bundling, it's a little bit different if you represent it as these one hot vectors, and if you would just add them up, then of course you get two hot vectors and things like that, and then you need to do this compression.
Oh yeah, and there are some properties that don't work, that work with binary or bipolar vectors, but don't work with phasors directly. So that's you're right.
Yeah, and I think the incremental binding is really important here. You don't want to have to know in advance how many vectors you want to bundle together. You just want to maintain the sparsity and just be able to use the vector at any point.
Absolutely, I think that's very useful and important. Any more questions? So last minute questions. So we are kind of already past 11 in my time zone. Okay. Well, I think we had a great start. What can I say? Indeed. So thank you very much, Graham, again for your talk. And so I copied the well, for myself, I copied the link that you provided to the code. I think it's very interesting to have a look at, as well as Alpha's paper, title of the paper, so which will appear shortly. Cool. Thank you very much. So I'll see you in 2 weeks. So stay tuned.
Okay.
Thank you.
Bye.
Bye-bye. Thank you. Bye.
Bye.
Cheers. Bye.
Bye-bye.
Bye.